Okay, so lab 4 bar magnets. My name is Cole Kepner. In this lab, basically what we did is we took some bar magnets, or a singular one, and treated it as a dipole, and basically moved the phone around and calibrated the magnetometer inside it to then find the magnetic field at different points along space, and investigate how the dipole field of the magnet basically affects the space. Now, we wanted to see firsthand how the magnetic field differed at different locations. And so as a result, we found out it's best represented as a dipole. And the dipole moment of our bar magnet was calculated to be 1.9 m meters squared. And so that was done observationally. I will be going pretty fast because I only have 5 minutes, but I think we'll live. Procedure. So first we calibrated the phone by basically sliding it across a straight line to find where the magnetometer was. Um, then we tested different locations horizontally from the bar magnet along the x-axis to see how distance changes the field. And then we went off-axis at a 45-degree angle and changed the location to kind of see how the curvature of the field worked. Main physics principles, the dipole magnetic field is up here. And then the exponent law relationship. So we then graphed all the relationships and data in an Excel sheet, and you will see the data in a second. So this is basically what we had. All the distances and fields were found here, and all the data is graphed on the right. In the next slide, we kind of have just a bit more detailed stuff. Off-axis field, blah, 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 as you do. Um, One note is that these are in microteslas, not teslas. Just error on the sheet. Calculation process. So this was to find the mu or dipole moment of our magnet. What we started off with was the equation in basically slope-intercept form. Slope-intercept. We got the slope, which is our n, and then k, which is ln k, was the intercept, and so we just do a simple calculation to find k. Basically e to the blank equals k. So that was that. R is 1 because we're sliding in a horizontal x direction, so it's r hat. Then we kind of simplify it down here because these are the same equation. Basically, they're equivalent because they're magnetic field. And then plug and chug down to the mu. System, magnet, and phone, surroundings, earth and table, meter sticks, initial conditions, R is 1. We kind of went over that already. The code, I just used the starter code. I think everyone did. You should have, hopefully. I hope. Nothing really crazy happening here. Just kind of create my vectors and arrows and copy and paste for the different locations. I'll scale it up to 2000 just to make sure we can see the arrows right. The picture of that graph, or the visualization, is over here. Now, what if? What if we hadn't oriented your experiment to compensate for magnetic north? Um, and so what if we did it just in a random spot? Now, if we didn't account for the Earth's field, then the Earth field would affect our data. And so it would point in a weird direction, and we would have basically the wrong magnitude on our magnet. Um, and so what if we were to stick two magnets together, end to end, and run the experiment again? How would that change? The field would double, but it would stay in the same direction because now we have two magnets contributing the same amount of field. But the direction didn't change because the magnets are basically in the same spot. It's just double magnets. And then possible error. So, I mean, between model real life, observational off-axis field, 7.667 times 10 to the negative 5. You saw that right down here in this corner. And then the computational field was found with the code right here. That is the basically vector for the field, but we can take that and we can just what do you call it? Find the magnitude by doing basically Pythagorean theorem. That yeah. And then assumptions made. Treated the bar magnet as a perfect dipole. Treated Earth's magnetic field is fully accounted for. Pretty self-explanatory. Human error. There are other electronic devices near the magnetometer, which was probably messing with the field. Obviously, it wasn't perfect, and there was human error in measuring stuff. So, thank you very much. Bye bye.